Okay, so in section 6.5, we're going to continue on the idea with the A's, B's, C's, and D's. This is what it looks like in general with our parent graph of the square root function. A square root B quantity x minus c plus d. Nothing new, nothing different, other than the fact that we have a new parent graph. Transformational form, ABCD. Okay, Chase?
Yeah, just got one my pencil.
Fumble?
Yep.
So, critical movements. The most critical point for every parent graph is? Thank you. That should be like church. Everybody should be able to say that the most critical point for every parent graph is the origin. It's never going to change. There are going to be parent graphs that don't go through the origin, and the origin is still the most important point on our graph, even though it's not on our graph. Okay? What should we pick for our rights? Let's start with rights on this. We're doing y equals the square root of x. What do you think I should pick for x? 1 and 4 and 9. Why should I pick those? They're perfect squares. So right 1 up 1, right 4 up 2. Right 9 up 3. Now you're welcome to go right 2, but then you have to remember up 1.41, 4. Why would you want to remember decimals? You could go right 3, then you'd have to remember the square root of 3. What is that, Giacomo? Yeah, me either. How about root 4? You know that one? Piece of cake, right? You want to remember right 4 up 2 or right 3 up 1.7? Me too. So if you stick with these from the origin, those critical points make it much easier to graph. What shape do we get? What shape is that? How did you describe it? Half of a parabola. It's a half of a sideways parabola. Is it a function?
Yes.
Yeah, it's a function. Half of a parabola that's sideways, that's definitely a function. Well, it is not half of an inverse function, it is an inverse function. It's the inverse of a parabola, y equals x squared with the domain restriction, x is greater than or equal to 0.
Oh yeah, because it can't be.
The next thing you want to be able to tell me is what's the domain for this function. Now the girl, and what's the range?
Greater than 0.
Or? No. This is an arrow at the end. This goes on forever.
Y is greater than or equal to 0.
Y is greater than or equal to 0. You're going to have to be able to identify domain and range. Okay? This is using set builder notation. You're also welcome to use the interval notation, which is what we should be using. So how do we say greater than or equal to 0? 0, comma. We're using interval notation. Infinity. What do I do next to the infinity? Shun the infinity, because you never get to infinity. So I should have retyped that green stuff and so it looks like the red. This is what you're going to do in red. This is set builder notation. All values of x such that x is greater than or equal to 0. You're going to say the domain is all values of x such that, and then you're going to go 0, comma, infinity, like this. That vertical line means such that. All values of x such that x is greater than or equal to 0. And for your range, all values of y such that, same thing, 0 to infinity. Now obviously it's not always going to be 0 to infinity. It's going to be wherever you start. It might go right, it might go left, it might go up, it might go down. It just depends on the graph. Any questions on this parent graph? Y equals the square root of x. It's the inverse of y equals x squared. Y equals x cubed. If you don't have this, if we really haven't talked about y equals x cubed, these are the critical movements. Right 1, up 1, right 2, up 8, right 3, up 27. You're never going to go right 3, up 27 unless you have a vertical stretch factor that's a fraction. And then it might squish it down. So 27 might be helpful. And then on the other side, it's left 1, down 1, left 2, down 8, left 3, down 27. This is like the problem Jane asked for from the homework. And that one had a squish of a third, so the 27 was used. Again, this is something you're going to want to know. Domain and range here. Your domain, all values of x, such that we go from negative infinity to infinity. In your range, same thing. Negative infinity to infinity. And one of the things that you should know, if your degree on your x is odd, your domain and range all reals. If your degree is odd, your domain and range will always be all reals, unless for some reason they restrict your domain. But in the parent graph, x cubed, x to the 5th, x to the 7th, x to the 9th, all reals left, right, all reals up, down.
How come here you're showing both infinities, but on the other one, you're only...
There's only one infinity in this problem here.
Oh, so you're always gonna...
You can never hug the infinity. That means you would get to infinity. Infinity is unattainable. Infinity is really just an idea. Why am I hugging the 0? Because it's greater than or equal to 0. So or equal to, you hug like this. And when you can't get there, it's greater than or less than, or it's an infinity, is always shun. Does that make sense?
Yeah.
So we can hug a number, but we can never hug the infinity. This is where we were, right?
Yeah.
Okay, everyone okay with that parent graph? Y equals x cubed. If I want to find the inverse of that, what do you do? So x equals y cubed. Solve for y. How do I do that? Cube root it. So we get the cube root of x is equal to y, right? X cubed, cube root of x, inverse functions. X squared, square root of x, the inverse functions. Here's what the cube root function looks like. You'll love the graph of this. This is what it looks like in transformational form, A, B, C, D. It's a flat S. And that's something you want to just kind of put into the hard drive. So when I ask you to graph any cubed function, your graph should be steep. The end should be pointing up and down. Cubed function. The graph is called the steep S. And you should be pointing up and down at the end. Any cube root function is a flat S, and your end should be pointing left and right when you're all said and done. And that's something that people kind of get, they start making the points, and then and all of a sudden their tail will start pointing up, because that's what cube does, but this is cube root. Okay? So A, B, C, D, nothing new there. Critical movements for cube root. What numbers should we pick for the left rights if we're doing cube roots?
8.
Like 8 is a good one.
27.
27 is a good one. 1 is a great one. Which one? Yeah, do we really want to pick 64 though?
Just those three.
Yeah, and really, we're just going to go with 2 of those. Because if you start going with more than right 8, you got to go right 27. That's hardly ever going to work. Okay, so right 1 up 1, right 8 up 2, and then what happens when we go to the other side? Left 1 down 1, and left 8 down 2. So when you look at the graph, from the origin, right 1 up 1, right 8 up 2, left 1 down 1, and left 8 down 2. Now, this is technology right here at its finest. Look at what the graph does here. So it doesn't have the ability to do the negatives. It thinks that the cube root of -1 is undefined, or no solution, or whatever it's thinking, because it's wrong. So there's your flat S. Again, there's arrows on the end, and the arrows are pointing left and right for a cube root. If you have an index that is odd, what's the next thing I'm going to tell you? What is it? And the range is all reals. So domain and range, if the index is odd, are going to be all reals, which means you're going to say all values of x such that we're going to go from negative infinity, which I can't fit this in here, you're going to say all values of x such that we go from negative infinity to positive infinity, and we shun them both. Really, we should probably put these in sets also. Calculate through, that's awful. So all values of y such that we go from negative infinity to positive infinity. If you have an odd power or an odd index, this is a guarantee. This is a guarantee. We're going to look at some graphs right now. What do I always ask you to do when we're graphing? What have I been asking all the time? Make a list. What's going to be in our list? Parent graph. What else? That's one thing. Translation vector. Oh, you're using 2 different ideas, right? So vertical stretch factor. So parent graph, translation vector, vertical stretch factor. That's all we need for the graph, right? In the list, you're going to need to add domain and range. Okay? So when we look at our lists, parent graph, vertical stretch factor, translation vector, domain and range. The order's not critical, but I usually put domain and range last and parent graph first. You do what you want. Yeah, these ones go right on those 6 graphs that you did, or 12. We're going to go through, in about 10 minutes, we're going to do about 10 graphs, 12 graphs. What's the parent graph here? Square root of x. Vertical stretch, 1/2. Translation vector, 0, 0. Very good. If there's no plusing or minusing, the translation vector is 0, 0. We stay at the origin. And domain and range, I usually wait till I can see it, but on this one you might know it just by looking at it. It's up to you. All values of x such that x goes from
Infinity to, no,
Yeah.
0 to,
and your range is going to be the same thing. If you don't see that from the equation, that's perfectly fine. Wait till you have the graph, and it'll make total sense to you. Starting at the origin, how do I get to my first point? Right 1, up 1 in the parent graph. What are we going to do? Right 1, up, 1/2. In the parent graph, we usually go right 4. In the parent graph, right 4.
Up 2.
Up 2. What are we going to do? Up 1. And just for fun, in the parent graph, we normally go right 9.
Up 3.
Up 3. We're going to go right 9 up
1.5.
1.5. So we would expect the graph to go through those points. We want graphing to be a mindless activity, no more T-charts. Follow your parent graph pattern, multiply the ups by the vertical stretch factor, and start wherever your translated origin is.
Now, if you had a different,
We're going to look at 10 more graphs, so just focus on this one right at this second.
okay, but if you had a different translation vector,
We're going to have one of those in just less than a minute.
would it make a different change?
Absolutely. Absolutely. That's why I usually wait till the end, because I'm a visual guy. Sometimes going from the equation, especially when you have a C and a D other than zeros, it's hard to visualize. Are we always going to go like this? No, sometimes we'll go like this. Sometimes you'll go like this. It's just a matter of what you have for a translation vector.
How would you, sorry, I guess
It's easier to do when you can see it than trying to do it from the equation. So this is another one. We're going back to cube root now. Parent graph y equals cube root of x. Vertical stretch, -3. Translation vector, 0, 0. And this one, you should never even have to hesitate at all. What's your domain and range?
infinities.
So, how do we say that? Not how do we write it, how do we say it? 2 words, all reals. If you have a odd index, it's all reals, so all values of x such that we're going to go from negative infinity to infinity. And same thing for the y's, right? Negative infinity to infinity.
When you say all of it, what do you mean?
I mean every number you can think of. Every single number that's on the number. That's what all reals means. Starting at the origin. How do I get to my first point on the cube root? In the parent graph, it's right 1, up 1. What are we going to do? Right 1, down 1, 2, 3. In the parent graph, we normally would go right 8, up 2. What are we going to do? Right 8, down 6.
Way down.
We're multiplying by -3. That's why we will end up going down, because of the negative. In the parent graph, normally it's left 1, down 1. What are we going to do?
Left 1 up 3.
Left 1, up 3. And normally left 8, down 2. We're going to go left 8, up 6. And of course, you should already know, based on my last one, that this is going to suck when we connect them, because the computer's stupid. Mr. Stedman called the company, and this programmer tried to explain to him why the cube root of -1 was imaginary. Imagine how that conversation went. Make sure you have both sides of a cube root function. Okay. See how this is a cube root, and the arrows are pointing left and right, not up and down. Sometimes students will come off this last point and they feel like, I should go up. It should do something like that, right? Not what we're looking for. Cube roots are flat, not steep. So they end up pointing left and right. Let's get a translation vector in here. Here we go. What's the parent graph for this one? Square root of x. Y equals square root of x. Vertical stretch.
-2.
-2. translation vector. Be careful.
3, 2, 3, 2.
3, it's the opposite of what's with the x is the c, and then whatever comes after is the d. You only switch the x one, not the y one. Switch for c, not for d. So when we graph this, we start at 3, 2, right here. To get to our first point in the parent graph of square roots, it's right 1, up 1. What are we going to do? Right 1, down 2. Parent graph is right 1, up 1. We have a vertical stretch factor of -2, so it's right 1, down 2. Where's the next point on the parent graph? Right 1, up 1, then right 4, 1, 2, 3, 4, up 2. What are we going to do? We're going to go right 4, down 4. What's the vertical stretch factor? Up 2 times -2 would be down 4. Yep.
Don't play with birds. Just play with it so that you can run.
Yeah.
You put 1 for x.
I'm not putting in a 1 for x at all. It would give you an imaginary
Oh,
number.
you're right.
That's why we don't use the plugins. I don't care what the coordinates of the points are. But the value that gave me this point was when I plugged in a 4 for x. So 4 minus 3 is 1. Root 1 is 1. Times 2, and then plus 2, or sorry, times -2 would be -2, plus 2 would give you that 0. But you don't want to play that game. What's that?
Logarithm's case, regularly we go right 1, up 1.
Correct. Right 1, up 1. Up 1 times -2 is, no,
Oh, -2.
down 2. That's why we're here. Right 1,
Yeah.
up 1 becomes right 1, down 2. Okay? When you connect the dots, here's your graph. Does everybody follow that?
From the middle point to the...
You never go from a middle point to the next point. Go back to the origin in your parent graph.
Oh.
Right 1, up 1. Right 4, up 2. Right 9, up 3. This is always from the translated origin. Never, you don't go to here and then from here do something. You go back to the origin. Does that make sense?
Yeah. It's only half because it's the input.
It is only a half. What do you mean?
The graph is only half.
Half a parabola?
Because it's the inverse of 5 x squared.
Well, that's true that it is, but it's only half a parabola because you can't go left, right? You can't pick numbers that, if you pick an x value that's less than 3, you get an imaginary number, right? We don't graph those. This is a real coordinate plane, okay? And why don't we have the upper half of the parabola? Because it doesn't work that way. It would have to be plus or minus the square root, and we don't have plus or minus. We only have the negative side. That's why it's the bottom half of the parabola. Let's look at one more. What's the parent graph? Cube root of x. Oh, wait. We forgot domain and range here. What's the domain for this one?
X such that it's
3, 2. Just the x's. 3, 2, infinity. And all the y's such that,
Don't include 2, right?
yeah, we include the 2. Sorry.
How do you know it's less than 2?
It is less than 2.
Oh, 2 to a negative.
So let's do the negative infinity first because that's smaller. Up to the 2, and we stop at 2. You always want to go least to greatest.
You don't include
It's not a million, it's infinity. If it was a million, yes, include it. But you can't. Oh, is that you're talking about the shun here? Yeah, so we don't want to. Come on. Good job. There we go. So we want to shun that infinity, negative infinity. Good call.
Why do you shun it? What's like the reason?
Infinity is not a number. Infinity is an idea. You can never get to infinity.
So you only,
It has to be or equal to include, to hug it.
okay.
Are we going to get to where y is 2? Do we get to a point on this graph when y is equal to 2?
Yeah.
Yeah, right here at this point. Do you get to a point, something comma infinity? No, there's no such thing because it's just an idea.
Okay.
Okay? What was the vertical stretch factor on this one? 3. Translation vector? -4, -1. Anyone not seeing those 3 components? Got a lot of sitters in this room. Okay? Domain? Domain? Negative infinity to positive infinity. There's no need to even look at the graph for this because it's always going to be negative infinity to positive infinity, both range and domain. Good luck. Okay? Kayla, you all right there? Should have paid for a better seat. At the old Boston Garden, they had seats, they were called obstructed view seats. And you would sit in the chair, and when you sit down and you look at the basketball court, the pole was right here. So you could only see this side of the court. Those seats were really inexpensive. Yes. Obstructed view. Well, least to greatest. All reals is all the numbers over here on the number line. Those are negative. Going all the way out to here, positive. This is the end. When you're starting on your y's, you're coming up and you stop right here. Where did we start? Negative infinity. We go up, 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 up. We can't go any higher than 2. The biggest number is 2. The idea is that we go to negative infinity. So we're negative infinity, 2. On the x's, we start at 3. We keep going to infinity. We just go in least to greatest. Okay, -4, -1. In the parent graph, it's right 1.
Up one.
What grade are we in? Right 1, up 1. What are we going to do? Right 1, up 3. In the parent graph, the next point is right 8, up 2. We're going to go right 8, up 6.
Okay.
Right 8, up 2. Right 1, up 1. Left 1, down 1 is going to become left 1, down 1, 2, 3.
You put all this.
I'm sorry?
I know you can go left and
You memorize this. These are parent graphs.
but
Do you have the parent graph for a cube root written down? Doesn't it say left? Do you have it written down? Because this guessing would be really bad right now. Does it say left 1, down 1? So I just want to make sure you have it. It's okay that you don't know it now, but just flip the page and look at it. Okay, so left 1, down 1 becomes left 1, down 3. And then left how many more? Left 8, down 6. Left 8. 1, 2, 3, 4, 5, 6. So when we hit the graph, obviously this is going to not work again. You're only going to get half of it. And then we'll add in the other half. Another shadow. Any questions on that? Yep.
Wait, why again is it a negative domain range? Like negative infinity?
Well, it's not just negative infinity, it's negative infinity to positive infinity. It's everything you can think of. There's no place on this graph that I can say, oh, we can't pick that x. You see that? Don't just go like this just to shut me up. If you don't see that x can be anything, go, I don't know what you're talking about. Is there a point on the graph where x is 1? You see a place on the graph where x is 1? Right here, right? Do you see a place on the graph where x is 2? Right here, right? How about 3, 4, 5? Is there any x value, when you move across the x-axis, is there ever a place where there isn't going to be a point above or below it? That means x can be anything. Look at this graph. Is there ever a place when I'm moving that I get to a point where there's an x value that doesn't have a partner y? How about the point negative 3 comma something? Do you see a point on the graph, negative 3 comma something? Can you come out and show it to me? Comma. That would be this point right here, wouldn't it? Is that a point on our graph? Look at our picture. You're saying yes, and I'm saying I don't see it.
Oh.
Here's my picture right here. Here's my graph. Do you see an x value of negative 3 for that graph? I don't see one. How about an x value of 0? I don't see one of those either. How about a y value of negative 1? Do you see a y value of negative 1? Here's where y is negative 1. Is there a point on the graph? Yeah. How about a y value of positive 1? How about a y value of 3? Yes, no? We have commitment issues, huh? Yes, yes, no, no. Yes, no. Do you have a boyfriend? Commitment issues. Here's where y is 3, right? Is there a point on the graph anywhere where y is 3? No. What's the biggest y can be? 2. That's a domain and range restriction. The biggest we can get to is 2 for the y's. The smallest we can get to is 3 for the x's. Yes. You can't pick anything to the left of that or above. Okay? The domain and range takes practice. We want to make sure we practice these. Okay? This is your assignment. If you don't have a calendar printed, copy it, clear your desk, and go back to your seat. Tony. Oh, I needed to do more. It's 2 o'clock. I gotta go. Let's get the lemon meringue and the strawberry. You get the strawberry.
Well, we love use calculator pedal.
If you use it, you're going to be doing things wrong. So you're welcome to use it all you want, but I would strongly advise against it. You are welcome to use a calculator. If you use it, you will be getting answers done wrong because you'll be using a calculator. I would highly encourage you not to use a calculator to determine these answers. You will get them wrong if you use a calculator. That's what I'm telling you. I'm saying the option is totally up to you. You won't get a 0, I wouldn't think, just because you use the calculator. But you will get problems wrong if you use a calculator to simplify them. 22. 23, my bad. Make sure you keep an eye on the indexes. Make sure you know what the index is when you're simplifying. It is imperative that you show work. If you don't have work, you're not going to get full credit.